Broken JSON is cheaper to prevent than retry. Use llama.cpp grammars in Python to stop invalid structures while the model is still decoding. This is the workflow you'll know how to run when we're done, which decodes llama responses while respecting a JSON schema so malformed tokens never appear. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. When you deploy LLMs to emit structured data, the most boring bug is the one that breaks parsing. A trailing comma or a stray token, and your downstream pipeline chokes. That means retries, firefighting, and noisy alerts. Grammar-constrained decoding moves validation earlier. It simply prevents invalid tokens from ever being produced, so your parsers never have to mend broken output. Here's the core idea. Instead of letting the model wander and checking the result after the fact, give the decoder a grammar that describes valid JSON shapes. The decoder then only picks tokens that keep the output valid. The payoff is fewer parse errors, deterministic fields like status flags, and much less repair logic later. We'll build a compact example. Ask a local quantized model for a JSON status object. Then walk 4 runs: raw output, grammar-guarded output, parsing into a numeric score, and finally a streaming low-latency approach plus a reusable helper. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, see the problem by running the model without any grammar guard. This snippet shows llama.cpp emitting raw JSON without any grammar safety, which mirrors what production systems see before validation. The Llama client loads a local quantized model into LLM, and the next assignment defines a plain language prompt requesting a structured object. The call to create completion runs the decoder with default sampling, so nothing blocks the model from injecting stray tokens or training artifacts. The text extraction targets the first choice returned, giving us the literal string the service must validate later. Increasing max tokens expands exposure to malformed fragments that the JSON checker still has to reject. The printed value reveals the malformed payload you would hand to downstream validators. Now show how a grammar blocks invalid tokens at decode time, so you never see malformed JSON. This example introduces llama grammar.fromJSON schema, letting llama.cpp filter every token against a schema before it ever hits your business logic. The JSON schema dictionary enumerates acceptable SVC values and forces a Boolean OK. So the grammar converter produces a compact GBNF fed straight into create completion. During decoding, the runtime now masks tokens that would violate required keys or property types, eliminating whole classes of repair retries. Because the call keeps temperature equals 0, the model stays deterministic. Raise it only if you need more variety, knowing the grammar still rejects illegal strings. The printout confirms the completion already respects both key names and value domains. Next, parse the guarded result into a numeric signal you can push to dashboards. This code takes the guarded completion and immediately derives an integer status score, proving the payload is ready for analytics. Wrapping create completion inside JSON loads works safely here because SVC grammar guaranteed syntactic correctness, while the schema definition ensured the Boolean exists. The parsed dictionary flows into int parsed OK times 100, yielding a percentage-friendly signal for dashboards or alerting logic. If you widened max tokens, you could request extra metadata fields without worrying about parsers blowing up, provided you extend the schema accordingly. The final print shows a numeric health score alongside the service identifier you can chart right away. After that, demonstrate lowering latency by streaming tokens while keeping grammar constraints. This snippet demonstrates how to stream llama.cpp tokens under the same grammar, so response latency shrinks for alert responders. The for loop iterates over each stream chunk, appending text fragments while the decoder remains constrained by SVC grammar. By checking for the closing brace and breaking early, you stop I/O as soon as the JSON object becomes complete, conserving both tokens and wall clock time. Keeping temperature equals 0 maintains deterministic structure. Nudging it upward introduces diversity, while the grammar still blocks illegal syntax. The printout reports how many characters arrived before the stop, and confirms the chunk ended with a brace. Finally, wrap the pattern into a reusable function for pipelines and monitoring. This example wraps the guarded call into generate status, delivering a reusable baseline component for incident pipelines. The helper asks llm.createCompletion for a single choice under SVC grammar, keeps the metadata returned with that choice, and decodes the JSON directly into a Python dictionary. Returning the parsed payload, together with finish reason, gives operators both the content and a stop cause signal they can log for monitoring. You can tweak max tokens or swap in a richer grammar without touching downstream code, because the function always hands back structured data. The printed line confirms the service status payload and the finish signal ready for logging, mapped to a real project. This toy example becomes a lightweight incident ingest. The same function can power health checks, automated runbooks, or structured annotations and logs. And it removes a whole class of parsing errors before they touch storage or alerting. Recap: grammar-constrained decoding filters tokens against a schema while decoding, so the model only produces machine-readable objects you can parse confidently. Use it whenever your model must emit structured data or when parse errors cost time. One caveat: you still need a correct schema, and if the grammar is too tight, it can block valid outputs. Next step: tune the temperature parameter to balance deterministic structure with controlled diversity, while the grammar enforces syntax. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.